Now, our problem this time, we have some tap water that's placed in the freezer, that has a temperature of minus 11. And so we get the rate of change of the temperature being this expression, minus kT plus 11. So if that's going to be our rate of change function, then this should be our function for the temperature at any particular time. So we want to show that that satisfies the equation. So we derive that function. We get minus k e to the minus kt. And we know we can manipulate a e to the minus kt to be equal to t plus 11. So we can do our substitution and we get our expression for the rate of change. So that's okay. Find the value of a. Well, the value of a, well, I think it's pretty easy to find that, because we know that initially it was 24 degrees. So we can get t is equal to 0, temperature is 24. So we can do our substitution and we get a times 1 and a minus 11. So our value of a must be 35. And then after 15 minutes the temperature falls to 10 degrees. So find the nearest minute for the water to start freezing. Well, we need this first part to find the value of k, and then we want what time it takes to get us to 0. So t is equal to 15, the temperature is 10 degrees. So we do our substitution there. Add the 11, gives us 21, divide by 35, and we get e to the minus 15k. So take our logarithm of both sides, we get minus 15k is natural log of 21 on 35. So k would then be minus 1 on 15, natural log of 30 on 5. Doing our division by 7 on both top and numerator and denominator. So then, what time does it take for the temperature to get to 0? So we add out our 11, we get 11 on 35. We're going to take our logarithm of both sides and get t as an expression of minus 1 on k, natural log of 11 on 35. So when we put our value of k in, put it on the calculator, we get 33.98, which to the nearest minute would be 34 minutes. So that's how we can do that problem. Our next one, we've got a graph. So again, as we look at that graph and go, wait on, that's an exponential graph, which makes sense when we look at the idea that the rate of the cooling of a coffee gives us that expression, which should give us an exponential expression for our temperature. So we can see that we're starting at 100 and it's approaching 22. So that's when we start to get our idea, well, A is going to be 22, because that's the surrounding temperature. As t approaches infinity, that part starts to become 0. So the A starts to approach whatever the value of t is. So that's where we get the 22. So, and that's what we see that the official expression there. So, proving the first part, we get our function for t. We can manipulate to get b e to the minus kt equals to t minus a, temperature minus a. The derivative of temperature with respect to time, so the rate of change of the temperature, gives us the minus k times b e to the minus kt, because the a is already differentiated to 0. And we can do our substitution to get our expression there. So the first part is done there. And that's where we find the values of a and b. So graph when t is equal to 0, we get the temperature being 100. And as t approaches infinity, the temperature equals 22. So that's where we get our value of a being 22. And when t was equal to 100, we get that the expression e to the minus kt would be 1. So the 22 plus b would be equal to 100. So b would equal 78. Then we get some data to find k. So 50 degrees after 90 minutes. Show that we can get that expression for k. So temperature's 90 times 90, temperature's 50. So we do our substitutions. Subtract 22 from 50 and divide by 78 to give us that expression. E to the minus 90k, take our logarithms, we get k is equal to minus 1 on 90 log of 14 on 39, which is the expression we wanted to get. Next, we want to find the rate of which the coffee is cooling after 90 minutes. Well, after 90 minutes, t is equal to 50. So we know that situation because we've just been told that. If that's the case, we can do the minus k, which we know what k is. T was 50. We had our 22 for A that we had there before, and we do that calculation with the value of k that we had in the previous part, and we get minus 0.3187. What does that mean? It means that because it's negative, it's cooling, and we've got 31 at 0.3187 degrees per minute. So that's the rate of change after 90 minutes. So next question, we've got a daily growth rate given to us by k outside of p minus 5,000. So show that p equals 5,000 plus a e to the kt is the solution. So again, we do that manipulation. So we've seen it a few times now. It's a very popular little question to ask. See if we can do that little manipulation. But it's pretty easy manipulation. So if initially p was 5,002, so t is equal to 0, p is 5,002, and then after 6 days we get 25,000. That allows us to get a and k. So t is 0, p is 5,002. We do our substitution. A would be 2 when we do that calculation. T is 6 and p is 25,000. Again, we subtract our 5,000 is the 20 divided by 2. Either 6k gives us 10,000 or k is 1/6 of natural log of 10,000. And find the mosquito population after 10 days. So when t is equal to 10, t is equal to 10, do our substitution. We had our k. There's our after 10 days, that's our population. Stay away from those mosquitoes because that's getting pretty large. This one, we've got a colony that increases 10% of the excess of the population over 1.2 times 10 to the power of 6. What does that mean? So basically, we've got an idea that we have a population, the daily growth being the 0.1, so 10% of the excess of the population of some population p minus the 1.2 times 10 to the power of 6. So whatever the population is, the excess of 1.2 times 10 to the power of 6. So that's what that expression means there. Excess of the population over 1.2 times 10 to the power of 6. And when the rate of change is 10% of that. So we've gone in that form. So if we're in that form, our k is 0.1. Our n is 1.2 times 10 to the power of 6. So our expression we can start to put into that form. So p n plus a e to the kt. So with that, if t is equal to 0 and the population is 2.7 times 10 to the power of 6, we can work out the value of a. So is e gets to the power of 0, and we had our 1.2 times 10 to the power of 6. Subtract that from 2.7 times 10 to the power of 6 gives us 1.5 times 10 to the power of 6. So there's how we can get our expression for a. So determine the population after 3.5 days. Well, after 3.5 days we can put that expression in, and we can get our value there for when it's 3.5. And the science checks the population every day. What's the first day in which you should notice the original population has tripled? So we're looking at 3 lots of 2.7 times 10 to the power of 6, which are our initial population. And we've got all our other values there. So we do the subtraction, and then we do the division by 1.5 times 10 to the power of 6. Gives us a value of, nicely, 4 2/5 equals to e to the power of 1.1 times t. So again, take our logarithm expression, and then we're able to work out t is equal to 14.8, which means after 15 days. So hopefully we've got a good idea of how all these questions work. The last few took a little bit more manipulation and a little bit more understanding needed to be able to solve them correctly. But all in all, they pretty much work the same way every time. Very similar to what we did with the 2-unit work. So be prepared to be able to use the similar ideas to apply it to whatever problem you're faced with exponential growth and decay.